All right, so we are recording. Audio and video is up. Everybody, let me get the slideshow up, and then I want to get to that question because that was a really good one. Okay, so everybody, welcome to Steel Design. We are on Lecture 10, and we are rocking and rolling. We're going to be talking about tension members today, and today we're going to have another example, and it's going to be almost like one for one what you did on your homework that was due today. The reason that I'm sort of repeating what you did on the homework is I want to review that process because I think it's very critical to what we do in the class, and B, I'm sure that if anybody has any questions about what you did on the homework, that the example that we do today is probably going to address them. And then we're going to go through the example probably pretty quickly because if you understood what we did on Monday, then what we're doing today is just more of that. Now, Mr. Adkins had a very good question, and I want to address that. I noticed something on the footnotes on the table. So if you go to table 1-1 and you look up some of the W8s, because the homework assignment that we had, we were looking at designing a W8 tension member. There are some footnotes at the bottom, and it says, things like shape is slender for compression with Fy equals 50 KSI. Shape exceeds compact limit for flexure with Fy equals 50 KSI. And I do want to talk a little bit about that. I'm going to use my prop here real quick. So, because it's worth talking about, and we've got time. So let me, give me a sec. So let's see. There's the little button. Okay. So, first off, those limits have nothing to do with tension members, and they're not going to affect anything that we're doing now, what we're doing on recent or upcoming homeworks or our first exam. In fact, they won't even really start mattering until maybe another month or so. But they are kind of important, and I want to explain. So let's say I have a column, and so the limits that we're talking about are related to elements in compression. So we're talking about columns and then beams, because if you bend a beam, the top of it, for instance, is in compression. Now, if I take this column and I load it in compression and I push on it, it will load or it'll accept load until it buckles. Okay. Now, if we talk about buckling, this particular mode of buckling has a name. We call it global buckling. So the whole column, kicks out. Okay. There is another mode of buckling which can happen, which is called local buckling. And local buckling is if you load the column in compression, it's not the entire column that fails. Maybe it's just the flange or it's just the web. And those are limits that are very particular in shapes where you have really thin cross-sectional elements. So thin plates or thin flanges, thin webs. And it's also, like, as a designer, it's usually something you really need to pay attention to when you're looking at plate girders, because with rolled shapes, most rolled shapes and particularly rolled shapes that are geared towards beams and columns and what have you, you're not really having to worry too much about that. I mean, I don't want to use alwayses and nevers, but usually those, in most instances, those are not a major issue. But in plate girder world, where you're tailoring the flange and the web size for the load demand, local buckling effects can really drive the design. So you really have to pay attention to what you're doing. There's a lot more math that goes along with plate girder design because of those various limits. But that's what those footnotes mean. They aren't really affecting anything now, but they'll affect some. So hopefully that answered your question. Is that good? Okay. It'll become much clearer when we start talking about columns. I'll bring it up because there is a particular check that we're going to do with columns that's directly related to that, and you'll see like where it comes into play and what properties in the manual dictate why that footnote's there. But we will get to that, I promise. Okay, so what we're going to do today is we're going to basically do another tension member problem. And again, it's going to be very much like what we did on the homework assignment. And so if you what you did on the homework, today we'll pretty much answer those. And like I said, we're going to go through those pretty quickly as a result. So, that's not what I wanted to do. I wanted to... technology. I wanted to go here, and I want to hit the slide advance button. Okay, so let's make sure we're clear on the step-by-step process It is? Hold on. Is it cutting out for anybody? Really? Huh. You know, it's funny you say that because I've been noticing it on my end. Like I'll be listening to a stream and then I'll hear everybody's audio. And I thought it was a Teams issue. Maybe it's a little bit more than that. Maybe it's my computer. But I'll after class I want to see if I need to do anything about that. Okay, if it gets really bad, somebody in chat just let me know. There might be something to that. Okay, so let's make sure that we're clear on the step-by-step process for design. So we're going to start off by computing a factored load, and then we're going to compute two values for design, a gross area and an R value. So basically we're solving for the properties that we're looking up. So, you know, what's the required gross area? What's the required radius of gyration? Based on those properties and based on whatever problem constraints that we have, we're going to select the lightest shape that's available. And then we're going to analyze that shape to verify its performance. And, you know, I say in particular the net section fracture limit state, but really we're just going to analyze all of them. But the big reason why we're analyzing it for tension members is because of the net section fracture limit state, because we're assuming a net area and a U indirectly because we're saying that the effective net area is 75% of the gross area. And we don't know if that assumption is correct until we go back and check it. And then finally, we're going to summarize the results and we're going to compute the efficiency. And so with that, we have our basically our next problem. Well, let me make sure everybody's clear on the formulas for gross section yielding, net section fracture. I threw this in there, but we're going to sort of gloss over this. One thing I will mention, though, is we're going to, this part right here. I want to talk about block shear because it's a little weird. It's not hard. It's just, it's kind of new and it's kind of funky. And I want to introduce the idea because Friday is going to be all about block shear. So if I can introduce the idea a little bit, I will. What I want to do today is do a tension member design, and we're going to do a rolled beam. We're going to do a W section. We're going to design a W12 today. So on your homework, you did a W8. But if you understand this, then hopefully if there's any questions on the homework assignment that you didn't understand or that were a little funky, that this problem will sort of, you know, illuminate those. So we're going to select a W12 section to resist a dead load of 130 kips and a live load of 110 kips. We're going to say that the member is 30 foot long, so that'll help us on the slenderness check. By the way, one thing I will mention, it is possible in the design phase that you just aren't given a member length. What if I just say select a W12 section, and you get to step 2 and you're like, well, wait a minute, I don't have an R value for design. Then just don't use it. Just, you know, select off of AG. That's possible as well. Remember, slenderness limitations, while they are highly recommended, they are just that, a recommendation. So it's possible that, you know, I give you a problem and I don't give you a member length. So just select off of AG design. We're going to assume A992 steel. That is the steel for W shapes that, unless otherwise stated, that's going to be what you assume. And we're going to use 7/8 inch diameter bolts. So pop quiz, make sure everybody's paying attention. If we have 7/8 inch diameter bolts, what does that mean for the connection? One inch. Well, it's a 7-inch diameter bolt. It's a 1-inch diameter hole. So the you know, physically we drill the hole a 1/16 of an inch larger, and then we add a 1/16 of an inch on top of that to account for you know, damage around the hole drilling. You're getting there, Mr. Romans. That's what I'll say. You're getting there. Okay. All right. So let me get out of this. Discard. Let's go to the notebook here, and let's get right to it. So let's write down what all we know. So we know, so I'll say member parameters. Man, my handwriting there, I can do better on that. Is the screen coming out clearly? Is there no, I know we had some audio issues, just checking to make sure there are no video issues. So we have a 30-foot long member. If it's 30 foot long, because we're going to be doing L over R calculations, we're going to be converting that to 360 inches. A992 steel. What does that mean? Like, what do I get from that? So we've taken that into account. We know that Fy is 50 KSI, and we know that Fu is 65 KSI. That's exactly right. So Fy is 50 KSI, and we know that Fu is 65 KSI. And we get that from table 2-4. And so that takes care of that. Oh, meant to use my highlighter there. And so we also have the 7/8 inch diameter bolts. So we'll say that, and that. So the diameter of the bolt is 7/8 inch diameter. And so we know that the effective hole diameter is 1 inch. Okay, so pretty straightforward. All right, so now we need to just go through step by step. So step 1, we need to compute our factored load. All right, so that means that PU, and again, here's our loads that, I thought I selected my highlighter there. Here's the loads that we're given. We're given a dead load of 130 kips and a live load of 110 kips. So I think by observation, this is another one of those instances where we can just say it's going to be 1.2 dead and 1.6 live. So 1.2 times the dead plus 1.6 times the live. And so 1.2 times 130 kips plus 1.6 times 110 kips. And I'll do this with you, but somebody in the chat help me out. Make sure I'm not totally missing some values here. I'll work for a living as well today. All right, anybody got a value for me? And by the way, I'm using my FE exam approved calculator, so I don't have my fancy TI-89 or anything. 332. Oh, do better on that. Come on. 332 kips. Okay, that's what I got. So we can keep on trucking. All right, so step 2, we need to compute our design parameters. Okay, so we have 2 parameters for design, but I'm going to do some stuff here on the side. So we have 0.90 Fy. So 0.9 times 50 KSI, which is going to be a value, and then 0.75 squared FU. So 0.75 squared times 65 KSI. Okay, so 0.9 times 50 is 45. And then 0.75 times 0.75 times 65. I'm getting 36.56 KSI. Do I have seconds on these? Am I doing these right? All right. So then we've got, our AG minimum or our AG design parameter, which is going to be the minimum of whatever these two are. So and then PU. So this is going to be 332 kips divided by the minimum of these two, which is going to be that one. So we're just going to use the 36.56. And what are we getting here? Somebody help me out. 9.08. Okay. And then we have our R design, which is L over 300. So that's 360 inches over 300. And I think I can do that one in my head, but maybe not. So that's why I have my calculator. I'm getting 1.2 inches. Okay. All right. I don't want to just barrel through all this, so I want to make sure this is clear. Is everybody with me so far? Any questions on, where we're at so far? Any concerns? Anything that you did on the homework assignment that was iffy? You let me know. All right, I'm gonna take that one. I'm gonna take that one as a yes. Okay, so now I need your help. So step 3, we need to select a member. So step 3, select a trial shape. And so for this problem, we really have 3 parameters. Okay, so the first is that AG design is 9.08. We have our design is 1.20 inches, but our third, so this is 1, this is 2, our third is that we're restricted to W12s. Remember, if you go up to the beginning, this problem says that we're limited to W12 sections. So those are going to be our 3 parameters. So try a W12 by, and then Mr. Riggs says try W12 by 30. Okay. Is anybody else getting that as the trial shape? So let's see. Okay. Oh, we got some challenges here. Hold on. So a W12 by 30 has an area of 8.79. So it's not big, or it's not big enough, right? So a W12 by 30 isn't going to work. But a W12 by 35 has an area of 10.3. So I think Mr. Wise might be right on that. Does that make sense? Because the AG for a W12 by 35 is 10.3 square inches. And then RY, which is the minimum, remember we're dealing with the W shape, the minimum for a W shape is WY, and that is 1.54 inches. Okay, does that make sense? Okay, now keep your manuals open because we're going to need a few more parameters. Okay, so first off, keep in mind that here's the shape. Here's the shape, and then, this is what we got going on. So somebody help me out. What other parameters are we going to need? Just looking at this. There we go. We're going to need a flange thickness. And that's a little difficult to read. what is the flange thickness for a W12 by 35? Anybody got a value for me? Come on. I know you could do this. I believe in you. I lost my bookmark. Everybody's quiet. Did my audio cut out on me? Okay, there we go. All right. Now, I'm going to look into the crystal ball a little bit. We are going to need some more dimensions. I'm going to go ahead and ask for BF and D. So somebody else tell me, other than the folks that have been responding, I want to make sure everybody's helping me out here. What is BF and what is D? So let's start with BF. Somebody give me a BF value. I want to make sure everybody's paying attention. Somebody that hasn't responded yet. I'll call on somebody. Let's see. All right, Farrah, what's BF? The BF, I need the BF right here for a W12 by 35. And then, let's see. All right, I'll let you off for now, but I got some other stuff to ask you. All right, how about Mr. Ball? What's the BF value? Okay, there we go. 6.56 inches. All right. There's too many cats over there. I think that's what it is. As an inside joke. Mr. Pelfrey, what do we got for the depth? Is Mr. Pelfrey out there? Where do you Okay, hold on. All right, this is why we're having it. All right, hold on. Okay, so what we're doing here is, you know, we're in this part of the manual where we're looking up the shapes, okay? And so we looked up the W12 by 35 because it met our gross area and our radius of gyration requirement. And now I'm just recording all the properties that I know I'm going to need in order to continue the rest of the problem. So I'm on page, yeah, as Mr. Bauer said, I'm on page 1-26. All right, you with me? All right, I don't think Mr. Pelfrey's there, though. So somebody help me out with the D value. What is the D for the W12 by 35? All right, here we go. All right. Okay, we've got some stepaways today. All right, so again, I want to make sure that this is clear. I don't want to be barreling ahead if you have any questions. So, yes, sir. Okay. This is, I'm glad you're asking this. So first off, the depth is not the only one that does that. There are, if you look at the flange width, the flange thickness, the web thickness, you'll see that all over the place. So remember, anytime those dimensions are listed, there are always two values. One of the values are going to be with decimals, and the other is going to be with fractions. The fractional values are what you would use for drafting and detailing. So if you were drawing this out in AutoCAD or MicroStation or whatnot, you would use the fractional values. The decimal values are what we use for design. And in design, we always use the decimal values. So just to use the depth, for instance, we're always going with the column on the left, not the one on the right. Oh, didn't mean to do that. So that makes sense? No problem. Now, keep in mind, this is a W section connected via the flanges. So we are going to need to take this section, split it into an equivalent WT, and look up that X bar connection, which is going to be Y bar. I think we've done that enough by now that we know that X bar connection for a WT connected via the flanges is the Y bar for the equivalent WT. So if I've got a W12 by 35, what WT section should I look up the Y bar for? There you go, a WT6 by 17.5. And what I'm looking for is the Y bar, which, as Mr. Riggs says, is 1.3 inches. Okay, so is everybody else okay with that? I don't want to barrel ahead. I want to make sure that we're good. So what we're trying to do there is we're trying to look up, this dimension here, that dimension there, which is Y bar. All right, there we go. You're right. Yeah, you're right. Okay, all right. So now what we're going to do is we're going to start analyzing that trial section. And again, if you got any questions, just stop me and let me know. Okay, so we're going to analyze the trial section. And remember, this is a trial shape. It could work, it could not. We'll see. It might, it might not. I don't know. So first thing we need to do is we need to compute the net area. So the net area is going to be the gross area minus what? What are we going to do for this problem? Somebody help me out. So we're going to subtract some bolt holes, right? So let's ask it this way. How many bolt holes are we going to subtract from this cross section? I'll scroll up a bit so we got a picture here. 4. And so we're going to have 4. And it's the diameter times the thickness, which in this case is the flange thickness, right? Because we're bolting through the flanges, right? This is, if here's the shape here of the camera, if this is the shape, we're bolting through the flanges. So we need the flange thickness right there. So this is 10.3 square inches minus 4 times the whole diameter. We figured out the whole diameter, that was an inch. And then this is 0.52. And so 10.3 minus 4 times 1 times 0.52. What are y'all getting? Everybody help me out with that. .08. All right. Okay. Now shear lag factors. All right. What shear lag factors are going to govern what cases? All right. Is there more than one case? Is it just a single case? Which cases are going to work? Okay. So we've got case 2. Any other cases? Case 7. There we go. All right. So case 2. All right, so let's do case 2. So we've already figured out the X bar connection. We sort of figured that out. That was Y bar. Why did I say 2.08? I don't know why I did that. You're exactly right. Wait. Hold on. Wait. Is it 8.22? Yeah. I think you're right. I think Mr. Thews led me astray. Hold on. Yep, it is. Yeah. So, sorry about that. So, yeah, this value right there, net area, that's 8.22. Okay. So, the X, going back to shear-like factors, we need the X bar, which is the X bar for the, or the Y bar for the equivalent WT, which is, it's okay. Hey, right here. A steady intake of it. So this is the Y bar for the equivalent WT, which was 1.30 inches. And then I'm going to cheat a little bit. Let me take this image here. So here's our cross section. So if this is our image, what is LCON? What's the length of the connection going to be? Maybe I'll make that a little bigger. That is a little tiny. Eight inches. There we go. So therefore, U2 is 1 minus X bar over L. So 1 minus 1.3 over 8. So 1 minus 1.3 divided by 8. Somebody got a value for me? I'm going to check and make sure it's right. Use my TI-36X Pro. There we go. Okay, so we'll call that, 0.838. Oh, that's close enough. That's one of the things in steel design is that, more often than not, is if you're getting your values to within a couple decimal places, you're probably fine because, just the way that a lot of our numbers work, the hyper laser precision isn't all that necessary. Okay, so case 7, we also need to compare the flange width to 2/3 of the depth. So the flange width. Let's see, what did we put? We put 6.56. And then 2/3 of the depth is 2/3 of, was that 12.5? Okay, and so 2/3, 8.33. So if I had to compare BF and 2/3 of the depth, that's certainly bigger. And if that's the case, what is U7? 0.85, not 0.8. You're because we're on K7, so that would be 0.85. And therefore, if U2 is 0.838 and U7 is 0.85, which one do we use? Do we use case 2 or do we use case 7? We use case 7 because remember, whenever we compute using case 7, we can use the larger of the two. So 0.85. All right. Everybody okay with that? All right. Okay, so now we can start looking at all of our limit states because we got everything that we need. So we have gross section yielding. So our phi is 0.9. FYAG, so that's 0.9 times 50 KSI times 10.3. Did I get, is that the right number? Hold on. Yeah. So 0.9 times 50 times 10.3. I'm getting 463.5. Is that correct? Okay. And then net section fracture. So 0.75 FU times the net area times U, so 0.75 times 65. The net area, I think that was 8.22. And then this is 0.85. So somebody help me out with that while I'm chugging this. $340.62. So this is definitely one where net section fracture governs. So that definitely is going to govern our design. And then while we're at it, let's just make sure that we're good on slenderness. So L over R is 360 inches over, and then our RY was 1.54. In all honesty, this one really is a formality, but because we know it works, but I like to get into the habit of doing this. So this ends up being like 233.8. I like to get into the habit of doing that because if you're going through a problem where you have to iterate multiple times, it's worth it at the end to just do it all and just to make sure that you've got it correct. Okay, so to summarize, if you remember PU, I think PU was like 332, I think it was. Yeah, 332. So PU is 332 kips, and PN is 340.62 kips. So the efficiency is PU over PN. And anybody have a number on that? $97.5%. So that's not bad. That's a pretty good number there. All right. So the efficiency is 97.5, and we know our L over R was 233.8. So use a W12 by 35. Boom. So hopefully that clarified. If there's any questions that you had on the homework, hopefully that clarified some things. I'm going to pull up the your homework assignment for today that's due Friday here in a second. But while I'm pulling that up, does anybody have any questions? All right, so on your homework assignment, this is your homework assignment, and I'm not done because I've got 10 minutes. And I want to talk about block shear because this is a topic worth introducing. But this is your homework assignment, and if you understood what we did today, what we do on this assignment is going to be very similar. The only thing that's worth mentioning is that for WTs, The RX is actually smaller because it's a different cross section. So don't look up based on the RY. Make sure that you're looking up based on the RX. Now, K7 will still apply to a WT as well as a W section, because if you read K7, it says, and I quote, WMS or HP shapes or T's cut from these shapes. So a WT section will apply, will comport with case 7 as well. And then for case 2, you're just using that Y bar because it's, how far is it from the connected face to the centroid? So it's just the Y bar. All right. Does that make sense? Rest of the day? I got one student that's good. All right. Okay, there we go. It's been seconded. All right, we're good. Okay, I want to talk to you a little bit about block shear because this is an interesting one. Okay, I'm going to show you a picture of it in real life and some cool models here because this is a unique one. All right, so this is something that we haven't talked about yet, and to be clear, block shear rupture is not something that you design for, but it is something that can happen. Okay, so normally the way that it works. So let's take all of the design problems that we've done up until now. You know how to design a tension member for gross section yielding and for net section fracture, and so we just did a problem, and so we ended up with a W12 by 35. What you would then do is you would take that W12 by 35 and check it for this. Now, what happens and it's surprising that it happens, but you can see here, here's an image of it happening in real life. Is so you have a let's say you have some member, right? And you've got some, just a series of bolts like this, what have you. What happens is block shear failure is sort of a combination of, you get a tensile failure along one plane and a shear failure along another. So if here's the member, right, and I'm yanking on it, this way, this is how I'm yanking on it, then what's happening is this plane right here is experiencing tension. But these planes over here, like this plane right there, that plane, and this plane, these planes are experiencing shear. And so what's happening is you're having this combination of a tensile failure and a shear failure, and you basically rip out this chunk of the member and you separate the member from the connection like what you see right here, okay? And that block ripping out and that combination of shear failures is why we call it block shear. So it's basically this combination of shear and tension, and it's a connection-related phenomenon that can happen that we haven't really talked about yet. And so it results in a block of steel tearing off, and that's why we call it block shear. So for instance, in this member, we have 2 shear paths and we have 1 tensile path. And it can happen not just in plates, but in a whole assortment of real life connection scenarios. So I got a little fancy here a little while ago, and I started getting on Inventor, and I drew some scenarios where this could happen in what we're dealing with in this class. So for example, here's one scenario. This is a channel, right? And so let's say you have a channel connected via the web. This is a scenario that we've dealt with, in this class. And so what can happen is basically that entire chunk, can rip out. And so what are you doing? You're basically, doing that. That entire chunk is sort of ripping out. So in this scenario, you've got this upper portion here, this upper portion there, and this lower portion here. See how it's sort of sliding along the block, so it's experiencing shear. And then this plane over there, where the these connections over here, this plane is experiencing tension. So shear and tension, and then that section rips out. So one of the things that we're going to have to address soon is how do we identify those failure paths, and then how do we go about computing the capacity associated with it. So like another example of this might be an angle. Okay, so here's an angle, and let's say you have the angle and it's only bolted on one side. And so what might happen is you might have, shear here, tension here, and then what happens? The section, rips out. And so you might have, something like this. Now keep in mind, you could also have a path that goes up, down, and then rips out that little chunk in the middle, almost that little strip out. That could be a potential block shear path as well. One of the things that you will see, and we'll talk about this more on Friday, is that you could have a situation where multiple failure paths could happen for block shear. But as we'll see, in the math, we'll find that sometimes some paths are more likely than others. And to keep it simple, the easiest way of describing it is the path of least resistance tends to be the one that governs. And what I mean by that is the following. Let me see if I can go back to my PowerPoint to kind of explain technology. So, for instance, if you had a plate like this, so let's say you have the same plate. So I'll draw the same plate over here, same plate over here. And let's just do 4 bolt holes. Same plate, okay? Now I'm going to draw 2 different block shear failure phenomenon, and then I'm going to show you why one would govern versus another. So one potential option is this. Ripping out that chunk. Okay, the other potential phenomenon might be something like this. Oh. And then ripping out that. Now, we'll call this scenario 1, this scenario 2. Of these 2 scenarios, I'm just curious from the chat, which one do you think would govern? Or which one do you think would be the most likely to happen? 1 or 2? Just, I'm curious what you all think. Okay, so we've got some split votes here. Oh, come on. There's got to be some other people here with some... Well, Mr. Spirichinski's absolutely right. The dimensions do matter. But let's assume this is all like one nice, even grid, All right, so most people are saying case 2, and case 2 is correct. Now, here's the reason why. If it's all about how much steel you're actually ripping through. So on case 1, you're having to rip through all of this, and all of that. So all that steel is having to be ripped through. But on case 2, that's on case 1. So case 2, it's just that and that. And assuming the dimensions are to scale, and again, my artwork might be a bit off, but I'm just ripping through less steel. See, that's a free edge right there. And same thing right here. So there's just less steel that I'm failing through. So case 2 is going to have a weaker capacity. So that's what's going to happen first. Mr. Adkins. Yeah, no, you're fine. So if you go to this angle, like you can see the way that I've drawn the block, there's a reason why it's not going up the other side of the angle, because that would be a bigger section to fail through. And if you understand why case 1 versus case 2 case 1 versus case 2, why case 2 would govern, then it might make it easier to understand this. So this is a W section connected via the flanges. This is the one that we just did. And the block shear failure path would look something like this. So for instance, if I, look at it on top, the idea is that, that part of the section would separate. And then, each of those 4 little chunks would rip out, because the alternative would be to rip through the center of the section, and that's a lot more material than just those little nubs on the end of each flange. So for instance, when we compute the block shear capacity for a W section connected via the flanges, what we'll do is we'll focus on each block. And so if we can compute the capacity of a single block, we'll just multiply it by 4, since there's 4 blocks, and boom, there's the block shear capacity for the entire member. Does that make sense? I got inventor happy, and I thought it would explain what was going on a little bit better. Now, we don't have time to get into the math and whatnot, so I'm going to save that for another day, or for Friday, but I will show you the expression that's in the spec. If you look at the RN expression, it kind of looks a bit nuts, because if you compare that to, gross section yielding, which is just FYAG, it's just that, and then you look at this, you're like, good Lord, what the heck is going on here? Because there's a pile of junk less than or equal to another pile of junk, and what's going on here? You would be surprised how easy this is. There's a lot of parameters, and there's a lot of little values that you have to compute, but this borrows off of everything that we've been doing up until now, because there's a lot of gross areas and net areas. The section properties are the same. There are some terms that are familiar. There is one thing that's kind of new, and we'll talk about this on Friday, and that's this 0.6. Like, what the heck is the 0.6 doing there? And there's a reason for that 0.6, but we'll talk about that on Friday. Right now, I guess I'm gonna have to call it, because we're running out of time. Any quick questions before we call it for today? All right. Well, I'm gonna stop the recording. Our Friday is block shear day. We're gonna talk about block shear. That's all I've got. I will see you all on Friday.